Fundamental probability examples. This is chapter 7. In this lecture, we are going to work different problems to see how the probability theorems, the counting of event rules, and the discrete and continuous probability distributions can be used to solve problems. So we know that the probability of event A is defined as the number of occurrences for that particular event divided by the total number of possible outcomes for that event. This problem says that a 104 key computer has been disassembled and the keys has been placed in a paper sack. If all the keys are in the bag, what is the probability that one of the function keys will be drawn randomly from the bag? We know that a computer keyboard has 12 of those function keys, and they go from F1 all the way to F12. So this is what we define as the possible of the number of occurrences. So our n sub A is equal to 12. That's the probability of those specific function keys in that total number of possibility. Now, we also know that the total number of possibility of the possible outcomes are 104 because there are 104 keys in that specific keyboard. So what we have to do is just divide 12 by 104, and the probability of that one of the function keys will be drawn randomly from the bag is equal to 0.115, or you can say 11.5%. From the different theorems, we know that the sum of the probabilities is always equal to 1, the probability of one event. So a manufacturer of pistons rings has 3 suppliers. In the stockroom, 20 steel rolls from supplier A, 30 from supplier B, and 50 from supplier C. So the question will be, what is the probability that the steel is coming from supplier A, or that the steel is coming from supplier B, or that the steel is coming from supplier C? So what we have to do is that we know that we have possible outcomes are either 20 from A, 30 from B, or 50 from C, and that is a total of 100. So having the total possible outcomes and having the individual outcomes or occurrence is the way that we can obtain the probability of those steel coming from supplier A, which is 20 divided by 100, from supplier B, which is 30 divided by 100, and from supplier C, which is 50 divided by 100. And remember this, the sum of the probability of one event is always equal to 1. If you add them all, 0.2, 0.3, and 0.5, that is equal to 1. Now, this is working determining the probability that an event will not occur. Currently, the stock room contains steel from suppliers A and B, 20 rolls of steel from supplier A, 30 rolls of steel from supplier B. If a roll was selected, what is the probability that a roll from supplier A was not selected? So we know that the total probability is always equal to 1. So to find the probability of not occurrence, we just subtract the probability that we know from 1. The probability of A is equal to the number of occurrence, which is in this case 20, because we have 20 rolls of steel coming from supplier A, divided by the total of possibilities, which is 20 plus 30 is 50. So what we do is subtract 20 divided by 50 from 1, which is equal to 0.6. So that the probability of not selecting a roll from supplier A is equal to 6% or to 60%, or 0.6. Mutually exclusive events. This is when we use the additive law of probability. And this is because we have the OR. So the probability of A or B is equal to the probability of A plus the probability of B. You're rolling a die. What is the probability that either a 2 or a 4 will come up? We know that the probability of 2 is 1 over 6 because there is only one number 2. And the total of possible outcomes are 6 because there are 6 numbers, 1 through 6. And the probability of 4 is also equal to 1 divided by 6. So the probability of either 2 or 4 will come out will be the sum of those individual probabilities. So it will be 1 over 6 plus 1 over 6, that is equal to 1 over 3, or 0.33, or you can call that 33.3%. Now, non-mutually exclusive events, and this is when we have one event out of one event. So the quality assurance class consists of 56 students. We have 12 females and 44 males. 8 of these females and 5 of the males are from out of state. So what is the probability that a student selected at random will be an out of state female or both? So when we have non-mutually exclusive event is when we have the probability of specific, which is in this case the probability of out of state, plus the probability of a female minus the probability of female being out of state. Okay, so the probability of out of state is 13 over 56 because there are 6 females and 5 males that are from out of state. If you add 8 times plus 5, that would be 13. So 13 over 56. The probability of a female would be 12 females divided by 56. Now the probability of both is 8 divided by 56, which is the female being out of state. So what you do is you sum the probability of female plus the probability of out of state minus the probability of a female being out of state. And that's equal to 0.303 or 30.3%. This is another example for the non-mutually exclusive events. And in this case, the problem is giving us the probability already. So in a local job shop, the P, the parts required plating is equal to 0.12, so the probability of that is 0.12. The probability of part required heat treating is equal to 0.29, and the probability of parts required both is equal to 0.07. So the question is, what is the probability that a part would require either plating or heat treating? Because this is theory number 4, we're going to be using the explanation of if event A or event B, which is in this case if plating and heat treating are not mutually exclusive events, then the probability of either plating or heat treating or both is given by the probability of plating plus the probability of heat treating minus the probability of both. So this is equal to 0.34 or 34%. Now moving to dependent events, and this is when we have 2 or more events out of 2 or more events. And this is specifically theory number 7, the dependent event, and this one says that the probability of A and B, and this is when we use N, which is the multiplication law, we have that is equal to the probability of A times the probability of B given A. This is means the probability of A and B divided by the probability of A. So going back to the QA class, so the QA class consists of 56 students, 12 females and 44 males. 8 of them are females and 5 of them are males. They are from out of state. So we have the N is 56, the females are 12, the males are 44. Females out of state are 8 and males out of state are 5. So if we select a female, what is the probability that she will be from out of state? So what we have here is the probability of out of state and being female. So this is equal to the probability of female and out of state divided by the probability of female. So this is the probability of female being out of state is 8 over 56, and the probability of female is 12 over 56. So this is equal to 0.668 or 66.8%. Independent events, and this is part of theorem number 6. A company purchases light bulbs from 2 suppliers. 60% of the light bulbs come from WT Corp and 40% from the NB Corp. Both suppliers have quality problems. 95% of the bulb from W2 perform as expected. 80% of the bulb from NB perform as expected. So what is the probability that a bulb selected at random will be from NB and that it will perform as expected? So in this case, we want to find the NB and those that perform as expected. So this is equal to the probability of NB times the probability of performing as expected for NB. So NB is 0.4, which is 40%, times 80 or 0.8, which is the probability of the NB performing as expected. And this is equal to 0.32 or 32%. So those were the different how to use the theorems of probability to solve problems. Let's go and check the counting of events. And this is using a simple multiplication. So witness to a hit and run accident, remember that the first 3 digits of a license plate out of 5 are, and noted that the fact that the last 2 were letters of the alphabet. So how many owners of cars will the police have to investigate? We know that the letters in the alphabet are 26. And because they are the last 2, that they remember the word letters, so we have 26 times 26. So they have to investigate 676 cars. Permutation, another counting of events rules. A sample of 3 is selected from 10 people on a Caribbean cruise. How many permutations are possible? So you have 3 out of 10. So this is a permutation because they can be arranged differently. And the order matters. So what you do is it's 10 factorial divided by 10 minus 3 factorial. So this is 720 possible permutations. Counting of events rules combination. Numbers available in the Illinois lottery are 1 to 54. On Saturday night, 6 numbers are selected. How many combinations are possible? And this is when the order does not matter, because what you want is those 6 numbers. It doesn't matter what order. Which is different from the Powerball because the last number really matters. So that will be a permutation instead of a combination. So for a combination, you have 54 and you have 6 at a time. So this is 54 factorial divided by 54 minus 6 factorial times 6 factorial. And the answer to that is the number of combinations that are possible to win the lottery. Hypergeometric distribution. So this is how we can use this type of distribution. To remember, the characteristic of the hypergeometric was that it have a finite population side, and also that there's no replacement. Once you take something out of that total population, you never replace that. So it means that the probability is always different. So you're purchasing a small lot of CRT test sample. Each lot contains 7, and you decide to sample 3 per lot and to reject the lot if there is 1 or more defective. So what is the probability that we accept the lot if the lot contains 1 defective CRT? So we know the best way to do this is understanding that every time that you get a sample out, the probability of that sample will be different. Okay, and you also know that you have a specific, you know what is the population size or the sample size. So for here, the population size is 7. You know that your sample size is 3. You know that the D, it will be 1 because that's what it will take to reject the lot. And D is equal to 0. And D is the number of non-conforming units in the sample. And D, capital D will be the number of non-conforming units in the lot. So what you use the formula, which is the C, D, and D, which is the combination of non-conforming units, times the combination of conforming units, which is the capital N minus capital D, and N minus D, divided by the combination of all units. You substitute and use the factorial and obtain the answer. And this is equal to 0.571, which is 57.1%. Using the binomial distribution, and what the characteristic of this binomial distribution, once again, this is a discrete type of distribution, and we have infinite sample size, and also we have a constant probability for the items. So 70% of the U.S. graduate students who earned a PhD are foreign graduates. Consider the number of foreign students in a random sample of 25 engineering students who recently earned their PhD. So find P, y equal to 10. So you know that you have an infinite because you don't know what's the population size. You know that specific information about it is that 70% of the graduates, so that was always constant. And you also have a sample size. So the data given here is the sample size, which is 25, and the probability of that specific situation, which is P is equal to 0.7. So what you have to do is to substitute this in the formula. And for this, you will use the C, which is of 25 and 10, then times P to the power of the Y, you're looking for 10, times Q, which is P minus 1, divided by to the power of 15. And this is because the way that you get 15 is N minus D, and N is the number in the sample, which is 25, and D is the number non-conforming in the sample, which is 10. So that gives you the 15. So this is equal to 0.0013 or 0.1%. The last example is using the Poisson distribution. And what we know is that we have the time of units, well, units per amount of time, or units per amount of volume or something else. So this one says that the average number of cars that arrive at an intersection is 1 per minute. So this is a specific amount of time or amount of location. So what is the probability that in a given minute the number of arrivals will equal to 3 or more? So this is the probability of 3 or more. That means the probability of 4 all the way to infinite. So the way that you do it is, because we know that the probability is always equal to 1, so you will set it will be 1 minus the probability of 2 and below 2. So this one you can use the tables. If you want to find the probability of that being equal to 2 or less, you can read it directly from the table, and that is equal to 0.9197. This is table C in your appendix. So subtract that from 1, and that will be equal to 0.0803. Now, you can also calculate it using the formula. So it's NP to the power of 3 divided by 3 factorials times E to the power of minus NPO. And you should get the same result. So once again, this was a short lecture to show how we could use the theorems of probability, the counting of events, rules, and the discrete probability distributions to solve problems.